Good evening.
We can start in a minute or two. I think they have a mock test 6 to 7, so they will be
Okay.
joining.
Yeah. Just let me know when I can start and I will start. Okay.
Yes, ma'am.
Thank you.
Thank you.
Good evening, everyone.
Good evening, ma'am.
Good evening.
Good evening, ma'am.
Good evening. Good evening. Okay.
We can start now, ma'am.
Okay.
Yes.
Thank you. Thank you, Usha. Okay. So what we are going to, good evening, everyone. Welcome to this session. Hello. Am I audible?
Yes,
Am I
ma'am.
audible? Okay.
Yeah,
Good evening, everyone, and welcome to this session. A couple of points regarding this session. This session is going to be more a revision session. It's not an interactive session, like it's not a problem solving session. However, I would take all questions. I'm not going to stop to take questions. May I request all of you to please use the chat box. I have my team members and they will convey to me any question that has to be addressed. I'll also be monitoring the chat box, but I do have my team members who are also going to monitor the chat box. So if there is something you do not understand, please use the chat box so that we can minimize disturbance and we can maximize learning. Is that okay? So you can use the chat box or you can you raise your hands and do things like that if you have a serious issue. Okay, so please use the chat box. I think the idea is to just maximize learning so that we minimize the amount of disturbance and everything. And just keep the chat box also, and may I also request that we use this chat box only with respect to doubts and clarifications with respect to this session. And we don't have any more personal comments or anything other than this session that is discussed, because that could also be a distraction. Okay, can we get started? So the agenda is to revise concepts of probability, conditional probability, and Bayes theorem. As you know that this was what you covered over a few weeks in the syllabus, and we are trying to do that here in a couple of hours. So it is going to go at a fairly fast pace. We are not going to go concept by concept, and it's not going to go at a slow pace. It is going to go at a fast pace. But if there is any concept that majority of you feel that I should spend more time, definitely spend some more time to make it clear. Okay. So the first conceptual understanding is why learn probability. As also mentioned in the lectures, the reason why we need to know probability is we are moving eventually to make, or we need to take decisions under a lot of uncertainty. And all of you would agree that no time other than the time we are currently living in, the time of the pandemic, re-emphasizes, and it actually tells us that it is very important that when we make decision making, we need to consider a lot of uncertainty. Okay. So in this uncertainty, we need a framework wherein we can capture this uncertainty. And what is the framework that would capture uncertainty? That is the probability framework. So we need to assign probabilities, which we call what is the chance of something happening in our day-to-day life. We are going to sort of formalize that chance into the language of probability. That is the reason why we need to learn probability, because eventually in your data science courses you need to try and tell something about the unknown using what you know, and typically what you know is very little, and you have to talk about what you do not know just by what you know. So when you are telling or you're trying to infer something about what you do not know using what you know, there is going to be a lot of uncertainty. Is this point clear? And that is why you are learning probability. Show of hands, please. If this is clear. Yeah, right. Okay. So that is the main reason why we need to have this an understanding of probability. Now, when we talk about probability, we start with building blocks of probability. Just as in any other subject, you have building blocks and you build a theory to understand it. You always give a structure. That's why they are called building blocks. Can you build a building without the foundation? It will going to collapse. So if you want to learn a subject, you need building blocks. And this foundation of probability is very, very crucial. The key foundational building blocks are the notion of what we call a random experiment. From a random experiment, we have what is a sample space. And once we know what is a sample space, we define what are events. So let us just revise these concepts. Now, first of all of us understand what is an experiment. An experiment is any process that produces an outcome. Okay. For example, I am going to perform an experiment where I try to see, okay, what would happen if two materials are mixed together? It produces an outcome. Yeah. But then after, what is a random experiment? The key difference between a random experiment and any other experiment is, even in a random experiment, we have outcomes. It is not that we do not know outcome. This is one of the most common misunderstanding people have, is when you ask them to define what is a random experiment, they say that a random experiment is an experiment where the outcomes are unknown. This is incorrect. In a random experiment, you know the outcomes, but you do not know which outcome is going to come. For example, when I toss a coin, I know the outcomes are head or tail. I do not know whether it's actually going to be a head or tail. So the uncertainty is in which outcome is going to manifest itself. Similarly, when I roll a die, I know the outcomes are 1, 2, 3, 4, 5, and 6. These are known. The outcomes are known, but what is the actual outcome is not known. So this is one key understanding which you all should have, is a random experiment is an experiment whose outcome is not predictable with certainty. Is this clear, please? The concept of a random experiment? Okay. Yes, so now, once we understand what is a random experiment, the next thing is to try and understand what is a sample space. So a sample space is the collection of all outcomes of a random experiment. So let's quickly go through a few random experiments. If I toss a coin, what are my outcomes? It is a head or a tail. If I'm again tossing two coins, I know my outcomes are going to be head, 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 tail, tail, head, and tail, tail. Suppose I'm having a race and I'm looking at the order of finish in a race with just three people. It could be either A, B, C. It could be A, C, B. It could be A, B, A, C. It could be B, C, A. It could be C, A, B, or it could be C, B, A. And you can see immediately when I am writing down the number of outcomes, this is why I needed to know what was permutation and combination. right? The minute I keep asking you what are the possible outcomes, I needed to know how to count. I needed to count whether the order was important. When I'm looking at order of finish, then the order is important. Whereas if I'm just choosing 2 people from 3 people, I can do it in AB, AC, and BC. These are the only 3 ways to choose it, and this will be the outcome of my experiment. Okay, so now suppose I'm looking at the lifetime of any instrument, then I know that that bulb can last any x where 0 is less than or equal to x is less than infinity. And if I'm looking at tossing a coin till I get a head, it could be a tail, it could be a tail head, it could be a head, it could be a tail head, it could be a tail head, and all of this. So you can see that this is an experiment of a sample space which has continuity, and this is a sample space which is infinite number of outcomes. So is the notion of a sample space clear?
Yes, ma'am.
I think the best way to calculate permutation and combination is to just keep practicing it. Okay, instructors have been doing it for quite some time, and that is the way. There is no, I am a person who refrains from giving any quick ways out. It is once you understand the concept and you keep practicing, it becomes very clear. Okay. So once you know how to give elements of a sample space and list the sample space, the next building block is that of an event. Event simply is a subset. So finally, you're not just interested in a sample space, you want to derive information. For example, if you go back to what we did, I toss a coin twice. I might want to know what is if I keep tossing a coin twice, I want to know what is the chance that the head always appears in the first toss. That is something which I want to know. I'm not interested in all the outcomes as such, but I'm interested in a particular outcome. So the way, or I might be interested in knowing what is the chance that both the outcomes are same. So these things I have to convert it. So the questions are converted into, so if I look at what both the outcomes are same, I know the outcomes that satisfy that question are HH and HT. In which head appears first? It's HH and HT. Okay, so you can see that all these sets are nothing but subsets of my sample space. So whatever I have asked as questions are translated into what I call events. To help me define what is an event is nothing but a subset of my sample space. So an event is just the collection of basic outcomes, and an event is a subset of sample space. Now, given what is an event, since I have called the sample space a set, and event is a subset of my sample space, I can define set operations on the sample space. By set operations, what are the common set operations? Union of two sets, the intersection of sets, and the complement of sets. These are the 3 basic set operations. Yeah.
Yes,
so when
ma'am.
we define these basic set operations, it is just not, let's not look at it from a mathematical perspective. When would I say union? If I am telling about A union B, what do I mean by A union B? For example, let me again go back to rolling a die, and my sample space is 1, 2, 3, 4, 5, and 6. Okay, let me define an event E to be the event that odd number occurs, and F to be the event an even number occurs. Okay, then how would I define the event E union F? How would I
All
define
numbers.
it?
That is, ma'am, S.
Either an odd or even.
Yeah.
Okay, intersection is an odd and even. Okay, so once you start expressing what is an event, you'll immediately know whether some events make sense and some events do not make sense. Does the event E odd and even make any sense to us? No. So you can immediately say that that is an event that will not happen. It's a null event. So then afterwards, complement. So what is a complement of an odd number happening? If a number is not an odd number, what is it?
Even number.
Even
number.
If
So that is what you need to understand is always keep practicing and articulating the events. One thing which I have noticed in my years of teaching is people just want to apply a formula and get away with it. That you can do if you're time constrained. But at a learning phase, you always train yourself to articulate, express it. And then you'll understand why you are doing what you are doing. For example, if you are looking at this particular thing, I'm choosing a number at random from 0 to 99. A be the event that the chosen number is an even number. Okay. So how many points would I have in A?
50.
50.
50,
Very
ma'am.
good. 50. Right? Okay. Right. And
Yes,
then
ma'am.
afterwards, the second point B is the chosen number is divisible by 3. Now, how many points would I have in this?
33.
33, because
33.
you can easily see 3 into 33 is 99 and 3 into 1 is 3. So I'll have this 33. That's a faster way for, I don't have to count. Agreed?
Yes,
If I
ma'am.
make
Yes,
it,
ma'am.
if I made it
Yes, ma'am.
999,
333.
so that is what you need to understand is just look at the problem carefully and then you can actually understand what is being asked. Okay. Now the question is express the event A union B. Express it. I'm not asking you to list down anything because what happens is even before we express, we are so trained to finishing a problem fast. I'm not asking for any this one. I want you to get into the habit of expressing the event. What do you mean by A union B here? I'm randomly choosing a number. That is the experiment I'm doing. Okay, right? And A union B is the event that the chosen number is. Complete the sentence.
Even number is
Even
either
number
even or
divisible by
divisible by
3.
Either an even number or it is
Divisible by 3.
3.
So this is what has to be the most important thing is you need to articulate what you're trying to say. Okay. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, let me ask you, how would you articulate neither A nor B?
Complement of A.
Even number and not divisible by 3.
27.
Again, be whole
English, in
complement.
English, do you use complements? You don't use complement immediately. Neither A is not happening, nor B.
Not
What does it
divisible
mean?
by 3.
Or,
Rest is
no,
27.
so
B is
first
not
let's
happening.
understand whether neither A nor B means. So neither A is happening.
B complement.
So is it either A is not happening or B is happening? A union B complement?
Yes.
This
Yes,
is
ma'am.
either A or B. So neither A nor B is A union B complement?
Yes.
Yes, ma'am.
Intersection
Neither A nor B
complement.
can be also
union B
A intersection B complement.
A
A
intersection.
intersection. No, 1 second. Listen to it carefully. Neither A nor B. What is it?
A complement union B complement.
A complement union B complement.
Yes. So now neither A nor B is A is not happening and B is not happening. That's what this means.
Yes,
Is
ma'am.
it
Madam,
clear?
yes, ma'am.
A
Now,
complement
A is
intersection
not
B
happening
complement.
as A complement intersection B complement.
It is same as A union B complement.
Yes,
So
yes.
neither A nor B is the same as this is either A or B complement. Is it clear?
Yes, sir. Yes.
Yes, ma'am.
Yeah.
So this is something which is very important. So go back to your class. I do not know whether it is class 10 or class 11 or whatever class. Go back to high school, look at your textbooks. I'm sure this neither and a and all of this would be very well written. Okay. So now once you can express them as sets, you find out what are the cardinality of sets. Why do we need cardinality of sets? We need cardinality of sets because we need to understand how to come up with a probability very soon. Okay. So now I said, what are the main set operations? It is the union, it is the intersection, and it is the complement. Now, there are two concepts which people keep getting confused with. One is people get a lot of confusion with disjoint events and independent events. And that is something which I'm going to try and clear today. Now, disjoint events, what are disjoint sets? Disjoint set
Null
is
set.
a set for which the
Intersection
intersection
is
is null.
null. Interest.
Okay.
Mutually
So what is the mean that disjoint and mutually exclusive? If A can happen, B cannot happen. That is what I mean by mutually exclusive. I repeat, mutually exclusive is if A can happen. If a head happens, can tail happen?
No, ma'am.
So
No, ma'am.
head and tail are mutually exclusive.
Yes, ma'am.
Yes, ma'am.
Okay. If an even number happens when I roll a die, can an odd number also happen?
No, ma'am.
No,
ma'am.
ma'am.
They are
No.
mutually exclusive. So
Yes.
mutually
Yes, ma'am.
exclusive means that I am excluding the happening of another event by telling that some other event A is happening, then B does not happen. The concept of disjoint and mutually exclusive are the same. So if an event is called a null event if it does not have any outcomes, and that is how you are representing this. Now we'll come very quickly to the concept of independent events because I don't want to introduce independent events without introducing the notion of conditional probability. But is the notion of mutually exclusive clear? This is not a solve with us. Okay, this is just a revision session.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So now the
Yes, ma'am.
complement of an event is the set of all events for which do not belong to a particular set. Now again, I'm choosing a number between 0 to 99. Okay. Again, neither A nor B, we have just seen is A complement, intersection B complement. I can easily find that out. And you can see we saw cardinality of A union B was 67. Okay. Right. And this is 33.
Yes,
Is
ma'am.
it clear?
Yes,
For those of you who feel skeptical, my only request is nobody is judging anybody here. Okay. No one is judging anybody here. You are asking a doubt to clarify your doubts. Okay. So why should anybody be judgmental about it?
Ma'am, I had a doubt in tutorial for the uranium question half-life. So in the tutorial, it was telling that the probability for the thing is n by 2 power k. Whole power k it should be, but they were just referring to it as n by 2 power k. It is one.
Okay, since I am not aware of this, I think this forum, can you please, Ishan, Mayur and Prasha are here. They will handle it later. Okay, I'm sorry, I'm not aware of this question, so I just think I'll just go ahead. Okay.
Okay, sure.
Yeah, right. Thank you.
Thank you.
Okay, so see now, why did we bring in the concept of Venn diagrams? The reason of why we brought in the concept of Venn diagrams was to just represent these events in a graphical way. And we already have learned in high school that whenever you have sets, a good graphical illustration of sets, especially when you're talking of set operations, namely the union, intersection, complement, you can always describe them or represent them using the graphical representation, which we refer to as Venn diagram. Venn diagram is a nice way to find out. So in us, a universal set is nothing but the sample space. So the sample space is represented by a rectangle. The events are sets which are represented by circles, which are subsets of your sample space. So here we have two sets, and you can see that the green area is the set E, the purple area is the set F, and the blue shaded area is your intersection, which is E intersection F. E union F is the entire shaded area, E intersection F is the shaded in blue. These two are disjoint events, and now you can see that in this, E is completely contained in F. Now, again, if you go back and see, why am I learning all of this in a probability class? Again, let me look at the sets. For example, I'm tossing a coin twice. I have HH, I have HT, I have TH, and I have TT. Let me define an event E to be head in the first toss. So these are my outcomes. Head in the first toss. Yeah. Now let me define F to be the event that at least one head happens. Right? Now, is this E a subset of F?
Yes.
Yes, ma'am.
Yes,
Right.
ma'am.
Now, suppose your interest, so the chance of this event happening would be less than the chance of this event happening. See, again,
Yes.
head in the first toss, and at least one head happens because there are more outcomes in the second event than the first event. So the chance of the first event happening is going to be less than or equal to the chance of the second event happening. Is that clear?
Yes, ma'am.
So these concepts, yeah, these concepts are the concepts which we are going to translate into probability. So once we introduce what is a set, what are the events, and we understand these as nothing but sets and subsets, we are in a position to define what are the probability axioms. The key probability axioms are, for any event, the probability of an event would lie between 0 and 1. 0 is less than or equal to probability of E is less than or equal to 1. The probability of a sample space is 1. What this translates to is nothing but definitely 1. Is my voice better now?
Yes, ma'am, it is
Yes,
clear.
ma'am.
Okay.
Yes, ma'am.
So the probability of the sample space is 1 means that definitely one of the outcome is going to happen. That is what probability of sample space equal to 1 means. Okay. Now, what do you mean by that? Is we have seen about mutually exclusive events. There is something called collectively exhaustive. What is collectively exhaustive is whatever I'm listing in the sample space, at least one of those outcomes should definitely happen. Okay, I cannot have any more events, that is any more outcomes. So the probability that says that the probability of the sample space is 1 means that one of the outcomes is definitely going to happen. I cannot have an outcome which will not happen, which will happen that is not in the sample space. The third thing is a very important property which says that the probability of your union, again, when I'm looking at a sequence of mutually disjoint events, this is a countable event, but for our simplicity, we just reduced it to see as what is the probability of 2 events. If 2 events are mutually exclusive, then I can say that this reduces to probability of A union B or even union E2. The probability of the union is the sum of probabilities. That's what it says. If I have mutually exclusive or disjoint events. So now this is laying the foundation to a very important rule, which we refer to as the addition rule in probability. So does this mean that if I have to find the probability of union, always I should have mutually exclusive events or disjoint events? The answer is no.
No,
We
ma'am.
saw that when I have probability of any 2 events, whether it is disjoint or not disjoint, what we saw was probability of E union E2 was probability of E1 plus probability of E2 minus probability of E1 intersection E2. Probabilities are not negative. In which lecture was probability negative? Can you please write an email and let me know that?
No, ma'am,
Okay.
it's
Yeah,
not
yeah.
in any lecture.
Probabilities can never be negative. It should always be between 0 and 1. Okay. So I can write this even union E2. I can write it as 3 disjoint sets. This is the first disjoint set. This is the second disjoint set, and this is the third disjoint set. And from this, in the lectures, you can see that we arrive at this additional rule of probability, which says that the probability of union of two events is probability of E1 plus probability of E2 minus probability of E1 intersection E2. Now you can extend this to many more events. Now, whether events are mutually exclusive or not, I don't think needs to be mentioned explicitly. If you should be able to identify whether even you should be able to identify whether events are mutually exclusive or not. Okay, for example, if I'm telling you, if I just tell you that E is the event of an odd, for example, you pick up a card from a deck of cards and I tell you E is the event of a heart appearing and F is the event of a club appearing. Are they mutually exclusive or not?
Yes.
Yes, ma'am.
Okay, so I don't have to explicitly mention. Unless I'm using that information of it being mutually exclusive for getting some other information, I don't think I need to mutually explicitly mention whether two events are mutually exclusive or not. Is that clear?
Yes, ma'am. Yes,
Okay.
ma'am. Thank you.
Right. Yeah. So now suppose I have 2 dice and this is something which we keep working on. I know there are 36 possible outcomes. Okay. Right.
Yes, ma'am.
Okay, these are the 36 possible outcomes. I have these as my 36 possible outcomes. Now let me define an event where the sum of the outcomes is equal to, sum of these 2 outcomes is equal to 5. How many outcomes satisfy this condition?
4.
What are they? 4, 1, 3, 2, 3, 2, and 1, 4, right? Sum of outcomes equal to 6.
5.
5. So what is the probability of the sum of outcomes equal to 6?
5, 1.
5 by 36. Again, you should remember that here every outcome is equally likely. So I can use the probability of equally likely to get hold of the probability here. Now, suppose I am defining an event sum is 7. What is the probability of that event sum is 7?
6
by
36. 6 by 36.
6 by 36.
What is the probability of an event that the sum is 11?
2 by
0 by 36. 2 by 36.
Now, what
2 by
can you say
36.
about these 2 events?
Mutually exclusive.
They are mutually exclusive.
Can I have a sum of 7 and 11 together? But suppose I
No,
define an event that 6 in the first row. Let me define an event G 6 in the first row.
1 by 36.
6
in
by
the first
36.
row.
6 by 36.
6 by 36.
6 by
36.
36.
Now, what can you comment about this event G and F?
They are not mutually exclusive.
They are not mutually
Mutually
exclusive.
exclusive.
Okay. Now, describe the event E union G and describe the event F union G. Describe it. I don't want any mathematical solution here. Describe it. E is the event that the sum is 6. G is the event that the first element was a 6. So how would you describe the event E union G?
Null set.
E union G, please.
Okay.
So it can be the sum can be either 6. That's the event, or the sum the first
element
be
6.
The first row is 6.
Is either 6 or the first outcome
element
is
is
6.
How would describe
Madam,
E intersection F G?
Zero, ma'am. Zero.
Null set.
First element is 6. The first
The
event
sum should be
first
6
is 6.
and the first element should be 6.
So now the reason why I'm insisting on all of you practicing this describing the event, the minute you describe the event, you know how improbable a particular event is. Can I have an event where the sum is 6 and the first is 6? First outcome
No,
is
ma'am.
6?
No, ma'am. No.
Okay, so
No, ma'am.
that is the main thing why you please keep practicing to spell out the events, describe the events. That way you're achieving two things. One is you're able to increase your understanding and not doing things mechanically. And second thing, especially if you go into applied areas, you will know, okay, let me describe it, and then you translate it into the mathematical framework. Is this clear?
Yes, ma'am.
Yes, ma'am.
That is something which I think you should always train to this one. Describe events. Listen to yourself. I think listening to yourself, even though it might be painful at times, is very useful. Okay, right. So the next thing is, so now typically one of the frameworks which is very useful when you are trying to compute probabilities, especially if more than one event is given, is to write it down in this table, cross-tabulation. Okay, now let me explain what is this with help of an example. Okay, now for example, I'm looking at this problem. In IIT, 40% of the students are girls. So I have here two categories. Okay, one is a girl and a boy, and the other is playing cricket and not cricket. Okay, how many people are girls here?
40.
40. So let me assume 40 and 60 boys, so 100. Okay. Now, what does this tell us? This tells us a person is a girl and plays cricket. Okay. This will tell a person is a girl and does not play cricket. Now, how many out of the girls play cricket? How many? What is the percentage of girls?
60%.
60%.
So how many girls will be here? 60%. What is 60% of 40?
24.
24.
This is 24. If this is 24, what would this be? This should add up to 40.
16.
16.
Okay. Now, similarly, what is the percentage of boys who play cricket?
42.
20. So this is 42. So how many people play cricket?
18. Oh, sorry, 42.
56, right?
No.
Add up
66.
these two.
Okay.
Okay, this is again 18. How many do not play cricket?
34.
34.
Right? So this adds up to 100. This adds up to 100. Is this clear?
Yes, ma'am.
Right?
Yes,
Is
ma'am.
this clear, please? Right. So now, once you put it up in this way, now what is this 24? Can you articulate what is this 24?
It is the number of girls who plays cricket.
A person who is a girl and who plays cricket. Right?
Yes, ma'am.
Similarly,
Yes, ma'am.
this is a girl and does not play cricket. So you can, now suppose I want to convert this into probabilities. What is the probability of, so I'm asking what is the probability of a girl and playing cricket? A person is chosen randomly. What is the chance that this person is a girl and plays cricket?
0.24.
0.24.
Yeah.
What is the chance that this is a boy and does not play cricket?
0.18.
0.18.
What is the chance that the person plays cricket?
0.66.
What is
0.66.
the chance that the person does not play cricket?
0.34.
Is it clear?
Yeah,
So
ma'am.
this is,
Yeah.
once you split it into these, especially when you have only two events and you can identify those events, okay, you can see that this A by N, it's nothing but the intersection of event E and G. Here I had a girl, I had a cricket, I had a boy, I had no cricket. Is that clear?
Yes, ma'am.
Yes, ma'am.
Similarly,
Yes, ma'am.
B by N, where total n is a plus b plus c plus d. You will get a plus b plus c plus d. That is E intersection H. This is F intersection G, and I have F intersection H. Similarly, I can find out what is probability of G, probability of H, and probability of E, and probability of F. So far, so good? Yeah?
Yes,
Yes,
ma'am.
Yes,
ma'am.
ma'am. Yes, ma'am.
Now comes the, once you have understood this, I have to introduce. So now we go back. The reason why I have introduced this table here is go back to this association between categorical variables. We had a similar thing and the concept of relative frequency.
Yes,
Row
ma'am.
relative,
Yes, ma'am.
column relative frequency. Now, when we talked about row relative frequency and column relative frequency, the row relative frequency is A divided by A plus B. Right? Now, this table is not only for what do you mean by mutually exclusive events?
If A happens, B cannot happen.
Yeah, so the E intersection F. So E and G are not mutually exclusive, right? This one is A divided by A plus N. There is they are not, E and G are not mutually exclusive. This is E intersection G, right? E intersection H. Is that clear?
Yes.
Yes.
But G and H are mutually exclusive.
Yeah, that is
right?
similarly E and F are mutually exclusive. Yeah, that okay. I'm not talking about E intersection F, right? The column wise and row wise, yes. Is that clear?
Yes, thank you.
Yes, ma'am.
Okay. So now, suppose I tell the following. Suppose this is a girl, this is a boy, and this is cricket, and this is not cricket. Okay. Now, how many girls play? I am choosing a person at random, and I find that person is a girl. Okay. So what is the chance with which this can happen? With whatever you have seen that here?
0.4.
0.44, or even here, given these ABCDs?
A plus B by N.
A plus B
plus
divided
B
by N.
Very good. Okay. Now, given that a person is a girl, what is the chance that the person, so now it is a relative frequency. How many girls do I have?
A.
How many
A plus
girls
B.
do I
A
have?
plus B.
A plus B. Of these A plus B girls, how many play cricket?
A.
A upon A plus B.
What is this A divided by A plus B? Express it. Express it. I don't want any formula or anything. Express it.
It's a probability of girl playing
Probability
cricket.
of girls who play cricket.
Yeah.
Is it a
Given
problem
that
and play crickets, or I know that the person is a girl? How many among girls, how many play cricket? Is it probability of a
Among
girl
girls, how
and
Yeah, among girls, how many play?
Yeah, among girls.
it is among girls, how many play cricket? Is that clear? So given that the fact is a girl, how many play cricket? Is that clear?
Yeah.
Yes, ma'am.
Yes, ma'am.
What was this? This was nothing but the probability of the intersection. Can everybody mute your... Thank you. Okay. Can everybody just look at this as this column was E intersection G. A was nothing but E intersection G by N, right? And A plus B is probable. So I have this A by A plus B. I can write as A given N by A plus B by N. Can I do this?
Yes, ma'am.
Yes,
And
ma'am.
what is A by N? Sorry, A by A. What is A plus B by N? It is nothing but the probability of the intersection, and A by N is nothing but it's a probability of event, and A by N is the probability of the intersection, right?
Yes, ma'am.
Yeah. So if I am asking what is the chance of a person playing cricket given that the person is a girl, that I have seen as probability of E intersection G divided by probability of E. That's what we have seen.
So it becomes a conditional probability as well.
It is a conditional probability. It is conditional probability.
Okay.
Okay. The way you can understand conditional probability, and since somebody has asked in the chat box what is the significance of marginal probability, Now, the way you can understand, I'm sure we have not covered this in our lectures, but I just will tell you what is a marginal probability is. If you look at this table, okay, these are events which are intersection, right? Now, what is an intersection? Both A, E and G is happening. That's what A is, the number here. This is both E and H happening.
Yes, ma'am.
Yes,
This is both F and G happening. And this is both F and H happening. Is that right?
Yes, ma'am. Yes, ma'am.
In
Yes,
other words, I can say that this number is telling what is the joint. Both E and G are happening jointly. Would you agree with me that I can rephrase it that way?
Yes, ma'am.
Yes, ma'am.
The joint
Yes, ma'am.
happening of E and G, joint happening of E and H, joint happening of F and G, and joint happening of F and H.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
These probabilities A, B, C, D, that is A by N, B by N, C by N, and D by N are referred to as joint probabilities. These are not marginal probabilities. These are joint. What is there here are joint. Now, this A plus B by N, that is what it is the probability of E happening. C plus D by N is a probability of F happening. Now, this are what we refer, and similarly A plus C by N and B plus D by N, which are on the row margin, these are on the column margins, and these are on the row margins, are referred to as marginal probabilities. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So these are the intersections.
Ma'am, I got the marginal probability definition, what you said, that A plus D by N, or C plus D by N, or B plus D by N, or A plus D by N. But what exactly practically, how we are going to implement? For example, the moment when you say joint probability, like E and G together it happens.
Yeah.
Similar E and H together it happens for joint probability. But what exactly, like, where you can practically implement?
So now see, if I'm given the probability of an event A and B happening, right, together, from given this event, I can find out if I know A and B, if I know, so this way, I know that probability of E happening is probability of E intersection G with probability of E intersection H. See, again, look at, see, if G and H are mutually exclusive. Yeah. Okay, I have G and H are mutually exclusive. We have already said that they should be mutually exclusive. So I can write G and H here. Now, if E is an event, what is this area? If this is E, what is the shaded area?
E
Intersection G.
E intersection G. That is this place, E intersection G. And what is this vertical line area?
Intersection H.
So I can write this E as E intersection G union E intersection H. Can I do this?
Yes, ma'am.
Now, E intersection G and E intersection H are mutually exclusive.
Yes.
Yes,
So
ma'am.
probability of E is going to be probability of E intersection G plus probability of E intersection H.
Yes.
Yes.
Yes, ma'am.
Precisely my marginal probability. I add these two, I get my marginal probability. So what is, so given the joint probabilities, I can, right?
Last one, can you please explain? Because this E is the universal set.
E is not a universal set. I have, see, G and H are, so this is the people who play cricket. These are the people who do not play cricket. Is that clear?
Okay. Yes.
So if this is the girls, I have girls who play cricket. The shaded area, what is the shaded area? It is the people who are girls and who play cricket.
Okay.
Yes, ma'am.
This area is the people who are girls and do not play cricket.
Do not play cricket.
So if I want to know what is the chance of being a girl, I know this event girl is G, girl and play cricket, union girl and does not play cricket, right? These two are mutually exclusive.
Okay.
So the probability of being a girl is a probability of this plus probability of this, right? And that's why I get A plus B. And this is what I have as the marginal probability of being a girl. Is that clear?
Yes, ma'am. Yes, ma'am.
Okay. So this
Yes,
is.
ma'am. Ma'am, one more. Ma'am, one more doubt.
Yeah.
In case of joint probability also we take two independent thing, and also in conditional probability also we take the
I've
two
not
things.
introduced what is independence yet.
Okay,
I'm
so
not introduced.
ma'am,
I talked about mutually exclusive. I've not
mutually-
introduced independence
okay,
yet.
mutually okay. So in case of joint probability, we take mutually exclusive events like such as E and G, and also in conditional
E and F,
probability.
not E and G. E and F.
Yeah, and at the same time, also in conditional probability, also we take the two mutual exclusive.
Conditional probability is the following. See, first of all, understand what is joint probability. Is the chance of this E is an event, G is an event. Okay, the chance of E and G happening together, that is joint occurrence of E and G. Is that clear?
Yes, ma'am.
Yes,
That is joint. Okay, now only the occurrence of E is the marginal. Only occurrence of F is the marginal. Only occurrence of G is the marginal. Only occurrence of H is the marginal. So far, so good?
yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. Now, if you're, suppose I restrict myself to only E. I'm given, I choose a person, I find that person is a girl. Okay, I want to know what is the percentage of people who play cricket among these. What is that? That is A by A plus B.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
But what was A? A was probability of E intersection G.
Yes. Yes. Yes.
A plus B is probability of E.
Yes.
That is how I can define my probability of G conditioned on E. What is the chance of me having this event G conditioned on E happening? Is that clear?
Yes. Yes, ma'am.
Yes, ma'am.
Yeah.
Yeah. Yeah. Thank you, ma'am.
Right. So I can define conditional probability are defined, and the formal definition for conditional probability is probability of the intersection divided by the probability. Okay. Now, how do I articulate this? This is the probability of an event happening conditioned on another event happening. Okay. Now, let me go back to tossing a coin, HH, HT, TH and TT, or let me go back to explain with the explanation of this dice itself. Okay, now let me define an event E to be the sum of outcomes is 7. Okay, now let me rephrase the question. Can I get an outcome of 7 irrespective of what is the first outcome? Can I get an outcome of 7 if I had a first outcome of 1?
Yes, ma'am. Yes.
Yes, ma'am.
That is
Yes,
1,
ma'am.
6. Can I get an outcome of 7 if the first outcome was a 2?
Yes, ma'am.
Yes, ma'am.
Madam, for all you
Outcome
can
was
get.
a 3.
Yes, ma'am.
Yes, ma'am.
How
For
first
all.
outcome was a 4.
Yes,
Yes, ma'am.
5.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So getting an outcome of 7, does it depend on what was your first outcome, or is it independent of what is your first outcome?
Independent.
It's independent.
Okay. Right. So suppose I define this as sum of outcomes equal to 6. Can I get an outcome of 6 if my first outcome is a 1?
Yes,
Yes, ma'am.
Yes, ma'am.
2?
Yes.
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 3?
Yes,
Yes.
ma'am.
4?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
5?
Yes.
Ma'am.
6?
No, ma'am.
No.
No, ma'am.
So getting an
Dependent.
outcome of 6, is it dependent on what was your first outcome?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes,
So
ma'am.
here you can see that now getting a sum of outcome is 7 was independent of whatever was your first outcome, whereas 6 was getting a sum of 6 was dependent on what was your first outcome. Is this clear? Understanding
ma'am.
wise? Okay.
Yeah, ma'am.
Let's find out what is the probability of these events. What is the probability? So first outcome is, let me call the first outcome. Let me say G is the first outcome is a 2. What is the probability of G?
6 by 36.
6 by 36.
36. What is the probability of E?
6 by 36.
6 by 36. What is the event E intersection G? Express it. I don't want any numbers here.
Probability of getting total of 7 when the first outcome is 2.
Outcome is 2.
So what is that probability?
1 by 36.
1 by 36.
1 by 36.
By 36. Is that clear?
Yes, ma'am.
Will you be kind enough to tell how 6 by 36 came?
In which one? First outcome is a 2. What are the outcomes where the first outcome is a 2? These are the outcomes.
Yeah, okay.
So how many outcomes do you have? 1, 2, 3, 4, 5, 6, 6 by 36. Yes. Right? Sum of outcomes is a 7. These are the outcomes. Again, 6 outcomes.
6 by 36. Okay.
Okay. So E intersection G is an outcome. Which is the outcome? It is only the first outcome is only this outcome satisfies both of them.
Yeah.
Okay. Now let's look at F intersection G. Articulated. What is this?
The sum is 6 and the first element is 2.
First element is 2. What is that element? What is that outcome?
2, 4.
2, 4.
4.
Okay. So again, what is the probability of F intersection G?
1 by
36.
1 by 36.
Okay, but what is the probability of G here? It is again 6 by probability of F.
6 by 36.
What is probability of F?
5 by 36.
5 by 36.
Okay. Now F so now is this clear how we are getting the probabilities?
Yes, ma'am.
Yes,
Yeah.
ma'am.
Okay. So now when would I say two events are independent of each other? Now just go back and describe what is this. This is the probability of A happening given B happens. Okay. And what is this? This is the probability of A happening. Okay. Now if A is independent of B, what do you think would happen to these two? What is the relation between these two elements, quantities? This is probability A happening given B happens. This is the probability of A happening. Okay.
Both would be equal to.
It would be equal to, because if, so now suppose I'm saying that this is the sum is 7 and this is the first outcome is a 2. Does the getting a sum of 7 depend on whether the first outcome is a 2?
No.
No, ma'am.
So this is the same as probability of getting a sum is a 7. But sum is a 6 when first outcome is a 2. Did that depend?
Yeah, ma'am.
Yes.
If probability of A intersection B is independent, that is if A is independent of B, then I know that this is going to be just probability of A. Would you agree?
Yes, ma'am.
If this is probability of A, then for any two events, I can write probability of A intersection B is the product of the probabilities.
Hello.
Yes, ma'am.
Right?
Yes,
so you can see that this is what I refer to as the multiplication rule. Okay. So if they are independent and given two events, I know if they are independent, this is the multiplication rule in general. But however, if they are independent, I have probability of E intersection F is probability of F into probability of E. Okay.
Ma'am, how does event of 6 depend on
So let's
event
do
of
that.
2?
What is probability of E intersection F? So let me go back to that. I defined E to be sum of 6, right? Sum of 7, right? Probability of E was what? 6 by 36. So far, so good?
Yes.
F is sum of 6. Probability of F was F by 5 by 36.
Yes, ma'am.
G is first row is a 2. What is probability of G? It is also 6 by 36. So far, so good?
Yes, ma'am. Yes, ma'am. Yes.
I'm saying to get a sum of 7, does it depend on what is my first row?
No, ma'am.
No, ma'am.
But a sum of 6, can I get a sum of 6 irrespective of what is my first row, or does it depend on what is your
It
first
depends.
row?
It depends on the
Depends,
first row.
ma'am.
Now let's check. So we
Ma'am,
notice.
sorry to interrupt you. Here it's not clear. Sum of 7, why it is independent?
Can I get a sum of 7 if my first row is a 1?
Yes.
Yes, ma'am.
Yes.
3?
Yes, ma'am.
Yes.
Yes, ma'am.
4?
Yes.
Yes, ma'am.
5?
Yes.
Yes.
6?
Yes, ma'am.
Yes, ma'am.
So I can get a sum of 7 irrespective of what is my first row?
Yes, ma'am. True.
Getting a sum of 7 does not depend. I can get it. I'm interested in knowing whether I can get a sum of 7 irrespective of whether it's my first row. But let's look at 6. Can I get a 6 if my first row is a 1?
Yes, ma'am.
1, 5, right?
Yes,
Yes,
you will
ma'am.
get.
2?
Yes, ma'am.
Yes.
3?
Yes,
ma'am.
Yes, ma'am.
4?
Yes,
Yes,
ma'am.
ma'am.
5?
Yes, ma'am.
Yes.
6?
No,
ma'am.
ma'am.
No.
ma'am.
So getting a sum of 6 depended on what was my first row. I cannot get a
Only a
sum of
6.
6 if my first row is a 6, right?
Yes, sir.
Yes.
Did you get it now? Is it clear now?
Yeah,
Yes,
ma'am.
ma'am. Thank you.
Yes, ma'am.
Okay,
So now
ma'am. Yes.
let's verify the formula. Okay. Now what is what is probability of E intersection G? We just saw. E intersection G is getting a sum of 7 and first row is this one. It is 1 by 36, right?
Yes,
2, 5, right? What is probability of E? 6 by 36.
6 by 36.
6 by 36.
What is probability of G? 6 by 36. Are they equal?
Yes, ma'am.
So they are independent.
Yes, ma'am.
Now what is probability of E F intersection G? That is also 1 by 36. We saw that.
Yes, ma'am.
Yes,
2,
ma'am.
4. What is probability of F is 5 by 36. G is 6 by 36.
36.
This is not equal.
Not it.
No, ma'am.
Is that clear? So now
Yes, ma'am.
when I have two events F and G, I say that two events are independent if probability of E intersection F is equal to probability of E into probability of F. And if they are independent, I know probability of E intersection F is, it's actually an if and
Dependent.
only if condition. But this is only for two events. Is this clear?
Yes,
ma'am.
Now somebody has asked that example of disjoint versus independent. Okay, right. Now I'm tossing a coin, H and tail. Okay. Now let's look at tossing a coin twice, HH, HT, TH, and TT. Is this clear? Now let me define E to be the event head in my first toss. What are the outcomes of E?
HT.
Let me define F to be the event tail in my second toss. What are my events?
HT.
TT.
TT.
Okay, right. Very good. Now, are E and F independent of each other?
Yes.
Yes, ma'am.
No.
Getting a tail in the second toss, is it independent of getting a head in the first toss?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Are E and F mutually exclusive?
No, ma'am.
No, ma'am.
No, ma'am.
No, ma'am.
Does that answer your question now, Srinivas? Disjoint versus independence?
But madam, what I'm saying is, see, when you differentiate between independent and disjoint, are we saying that when you do the first toss, if it is heads, the second toss is also independent of what happens in the first?
Yes. So the question I'm asking is, what is the chance that you get a tail in the second toss given the first toss was a head?
Yeah, it has an equal chance.
Yes. So the chance that you get a tail in the second toss is independent of whatever was your first toss, right?
Right. But that is also not related to what happened in the first toss. So is that not, they are exclusive, isn't it?
I didn't get your question, please.
No, the first toss and the second toss are in a way they are independent. But
okay, let's forget about the first toss and the second toss for now. Okay. Let me just look at a single toss.
Okay.
Okay. Now, are H and T disjoint? Happening of a head?
Yes, ma'am.
Yes. Are they independent?
They are,
If I get a head, can I this one? Are they independent? If I get a head, if can T?
they are not independent,
Madam,
because if you get a head,
you cannot get a tail, right?
yeah.
Okay, in the
Yes,
first toss. Yes.
Is that clear?
Madam, for independent events, we need to have at least two observations.
So,
Yeah.
ma'am, can I say? Okay, go on.
If E is an event of getting a head and F is an event of getting a tail. Okay, in this case, it was difficult for me, but look at two tosses. It is simple. You can understand that. Or let's look at again, let's go back to this. Can you explain with respect to rolling a dice, since we have looked at this example?
Madam, the disjoint concept we can explain using a single toss or single roll of dice, right? But for independence, we need at least two of them.
Not really, right? Suppose I have S equal to 1, 2, 3, 4, 5, and 6, right? Okay, and I can define event E to be a odd number.
Yeah,
and I can define F to be a multiple of 3. Okay. Now are E and F disjoint?
No.
You can define it. It's not only for a singleton event or something.
So disjoint is fine. I can pick any number out of the sample set.
Given I choose a number, okay. In this itself, I can say given a number which is a multiple of 3, what is the chance it's an odd number? Does that make sense to you? I can define an event of that kind, right? I take a number and I find it is odd. What is the chance it is a multiple of 3?
Yes.
1 by 6.
1 by 6.
1 by 3.
No,
1 by 3.
I'm not asking the number. I'm saying, does this make sense?
Yes, it makes sense.
Yes, ma'am. It makes sense.
Yes. I don't have two sample spaces, just one throw of a roll of a die, right?
Yes, ma'am.
Yes,
Is
ma'am.
it clear?
Yes.
Yes, ma'am.
Right. So
Yes, ma'am.
that is what you need. So that's why I keep repeating. Don't jump into solving a problem. Understanding is key. And this course, we are focusing on understanding the concepts. Is it clear, please?
Yes.
Yes,
Can I
Yes,
can I
ma'am.
say that that if two events are mutually if they're say mutually disjoint exclusive, then it is not, it can never be independent, right?
No. Why can't it be?
Because if they are independent, then they are occurring simultaneously, then I can define independence. So it cannot be mutually exclusive at the same time.
I didn't get your question.
Like if two events are independent, I am saying, then I am defining that probability, like in terms of conditional probability, that given A given B is equals to probability of A. So I am taking that it is simultaneous is happening like that. So then how can it be exclusive, like disjoint?
Madam, because if they are disjoint, then basically happening of one is ruling out the happening of other. So there is kind of dependency in there.
So can I say that, like if like here in the rolling of a dice, I am rolling say 2 dice simultaneously, then I am getting it. So if I say that they cannot be disjoint, like then simultaneous occurrence is not there.
I think in a single dice, you can say in a single dice.
Yeah. No, that is because if they're disjoint, your probability of A intersection B will be equal to 0, right?
Yes, ma'am.
Yes, ma'am.
And you know from your this one, the probability of A conditioned on B is probability of A intersection B divided by probability of B. If this is going to be 0 in disjoint, I cannot, this is automatically become 0, right? Conditional probability.
Yes.
Is it clear?
Yes.
Right?
Right.
Is it clear now?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Sunand, I do not know what is a uranium problem. I'm sorry. Okay, so I think I need to leave this for my team to discuss. Okay.
Okay, ma'am.
Right. I'm sorry. I do not know what is a uranium. I don't have problems here. It is a very small brain. It does not contain a lot of problems here. Okay. Yeah. Right. So is the multiplication rule clear and the notion?
Just one
Yes,
last
ma'am.
part, ma'am.
Yeah. Sure, please.
In this particular, the last page that you had, if we want
This
to
one? This one
yes,
or yeah.
yes, ma'am, this one. If we want to equate the last line, we will have to take the conditional probability in the second part, right?
See, first of all, you don't equate anything. Okay.
Yeah. Sure.
It's only the data. Whatever is the data, you verify whether something happens or not. Okay. Here, what we have done is we have verified. What is it we wanted to verify? We wanted to check whether F and G are independent of each other. That is what we wanted to discuss. Is that clear?
Yes.
So now what is F? F is the event of the sum of the outcomes being 6. I know that the sum of outcome being 6 is dependent on what is your first row. This is something which we discussed without any math involved.
Right.
Okay. Right.
Yes, ma'am.
So now I want to verify this. So how do I verify it? I need to check whether this probability of F intersection G is equal to probability of F into probability of G. I know they are independent. That is what this says. This is what is my, if two events are independent, this should happen for two events, right?
Yep.
Yes, ma'am.
Okay, so but if it happens that I know they are independent, if it does not happen that they are not independent, I get probability of F intersection G is 1/36, and this is going to be 5/36 into 6/36, which are not equal. So I know F and G are not independent. So in some way, I'm validating what I argued without any math.
Okay.
Is it clear?
Yes.
Yes, ma'am.
Yeah. Is it clear, please? Right. Okay. So, but one word of caution is this events, right? When I talk about the event, probability of the intersection, just as the addition rule for disjoint events is probability of union is sum of probabilities. This was for mutually exclusive events. For independent rule, it's called the multiplication rule. The probability of intersection is product of probabilities. Is it clear? This is for mutually exclusive or disjoint. This is for independent events. This is an if and only if condition only for two events. Is it clear? When I have two events, if probability of E intersection F is probability of E into F, and vice versa, if probability of E intersection F is equal to probability of E intersection F, that's all. This is the converse condition. Then I say E and F are independent of each other if and only if this happens. Is that clear?
Yes, ma'am.
Yes,
But
ma'am.
when I go to three events, we saw that again, you go back to the lectures, we see when we look at three events, we saw that this rule is slightly more difficult when it comes to three events. I have to say that we can say that three events E, F, and G are independent of each other if the following happens, that is, the probability of the intersection is the product of probabilities. That's the first thing, but that alone is not sufficient. I need to check what I refer to as pairwise independence. What is pairwise? How many pairs do I have if I have E, F, and then G?
3 pairs.
Three pairs.
Three
So
pairs.
the pairwise, what are the pairwise? E and F are independent, E and G are independent, and F and G are independent. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes,
Yeah.
ma'am.
So if you look
Yes, ma'am,
at your questions, so this will help you understand independent or disjoint events. This was, I think, a similar question to what you have done in your practice assignments, if I'm right. Okay. Now, what is E1? What are the outcomes of E1?
557, 575, 755.
Why will it be 755 also? The first digit is 5, right? In 755? If it is 5
digit of the number.
So the first digit.
E1 just.
In 755, will it be this one?
Okay, sorry, ma'am.
Right? What is E2?
No.
Only one,
755.
755 also, right?
Yes.
75.
What about E3?
575,
575,
755.
Now let's understand the disjoint part because that is easier. Are E2 and E3 disjoint?
No, there is a common.
No, ma'am.
No, ma'am.
E1 and E3 disjoint?
is common.
No.
No, ma'am.
No, ma'am.
No, ma'am.
No, ma'am.
So this is not there, this is not there. Okay, now let's look at E1 and E2. Okay, are they independent?
Yes.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, without doing the math, just talk to you. See,
All
the
three.
chance that the first number is a 5, is it independent of whether the second number is a 5?
Yes.
Yes,
Yes,
ma'am.
ma'am.
Similarly, the chance that the first number is a 5, is it independent of the third number being a 5?
Yes.
Yes,
Yes,
ma'am.
ma'am.
So, all you need to do is verify whether this is true.
Yes.
Yes, ma'am.
Yes, yes.
Now, what are E1, E2, and E3? If the
All
first
three
number and second numbers are 5, and the third numbers, are they independent? This is something which you can check. Okay. So pairwise independence and E1 union E2 union E3. That's how E1 into E2 intersection E3. Okay. Check that and you can see that the answer is only A and B. Is it clear, please?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So the next concept.
Ma'am, can you explain the why C wouldn't be there?
Which C?
Ma'am, the E1, E2, and E3 are independent. Can you explain? Independent? Can you explain that?
Okay. What is E1 intersection E2 intersection E3?
Null. It's a null, ma'am. Null set.
But can you express it?
All three numbers are
5.
All three digits. A number with all three digits 5, ma'am.
5.
I don't have anything in this, which is 5, right? Now,
Yes, ma'am.
if they have to be independent, I need to check whether probability of E1 intersection E2 intersection E3 is equal to the probability of E1 into probability of E2 into probability of E3. That is not happening.
Yes.
Yes, ma'am.
Okay.
Yes, ma'am.
No.
Is
Yes,
it clear now, please?
Okay, ma'am. Yeah.
Yes, ma'am.
Yeah.
Yes, ma'am. मैम मतलब यहाँ पे हम कन्वर्स चेक कर रहे हैं.
So yeah, for 2 or
It is
more independent,
if this happens, right?
The intersection product
The
of
the product, it is not happening, right? It
Yeah.
is independent. We are asking if it is independent. If this is independent, if that happens, right?
Yes,
Yeah.
ma'am.
Okay, ma'am.
Yeah. Is it clear,
Yes, ma'am.
please? Yeah.
Yes, ma'am.
Yeah.
Okay. Now the next law is what we refer to as the law of total probability. Now the law of total probability is the same thing. I suppose I have F. This is F complement. Is that right?
Yes, ma'am.
This is my universal
Yes,
set.
ma'am.
This is an event F. This is my F complement. I can write this E as E intersection F union E intersection F complement. That is this area plus this area.
Yes, ma'am. Yes, ma'am.
So my probability of E is going to be probability of E intersection F plus probability of E intersection F complement. This comes from my addition rule because they are mutually exclusive.
Yes, ma'am.
Yes, ma'am.
Right? Now this from my probability multiplication theorem is probability of E conditioned on F into probability of F, my multiplication rule.
Yes, ma'am.
And this is going to be probability of E conditioned on F complement into probability of F complement.
Yeah.
Yeah.
Right? Okay. So I have probability of E is probability of E conditioned on F into probability of F plus probability of E conditioned on F complement into probability of F complement. I can write this that way.
Yes.
Yes, ma'am.
Okay. So that everything follows from here only, right? Now, if I have instead of F and F complement, if I write this as F1, this is F2 and F3, what would happen to my formula then? If instead of, if I had this as E, I had F1, F2, F3. Now what would this is, what is this area? E intersection F1?
Intersection.
This is E intersection F2?
Intersection F2.
Yes, ma'am.
This is E
E
intersection
intersection
F3?
F3.
Yes.
So I can write probability of E as probability of E intersection F1 into probability of F1. I skipped a step in between. E intersection F2 into probability of F2 plus probability of E intersection F3 into probability of F3. I can do this, can I?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now I can keep doing this. If I have F4, I'll get another F4 thing.
Yes, ma'am.
If I have F5, I can keep doing it. So if the only condition is if these should be this F1, F2, Fk are mutually exclusive. That is an important condition. Is that clear?
Yes, ma'am. Yes,
Then
ma'am.
I can write for any event. So this identifying what are mutually exclusive is very, very important. Is it clear? For example, again coming here, look at the first problem. What are the mutually exclusive things here?
Girls and boys.
Girls and boys.
Cricket and not cricket.
And cricket and not
And
cricket.
yeah. Cricket and
Not
non-cricket.
cricket. Is that clear?
Yes,
So
ma'am.
identifying this is very important. Okay, so this is 40%, this is 60%. Now, what is the 70% of boys play cricket? What is this probability? 70% of boys play cricket.
Intersection of
Intersection,
B
ma'am.
and C.
The probability of boys playing cricket is 0.6, right? So I want to know what is probability of boys intersection with cricket. Now, what would that be? That would be the probability of cricket playing boy into probability of boys, which is 0.7 into 0.6, which I've already found out to be 0.42. That is, I put it as 42 people here. Is it right?
Yes, ma'am.
Similarly, probability of G intersection C, I can write it as C given G into probability G, which again I saw was 24. Is it right? 0.6 into 0.4?
0.4. Yeah.
Yes, ma'am.
Ma'am, here I have one confusion. I often confuse between the intersection and the conditional probability. Like here, B intersection C means boy and playing cricket.
Yes.
And the letter is probability of C when B is happening. It's also like the same thing, no? Then
Just forget about conditional. What does this say? 70% of the boys play cricket. Right?
yes, ma'am.
How many boys play cricket?
70%.
How many boys play cricket?
60.
Out of the 60, 70% play cricket, right?
Okay, yeah.
Is it clear?
Yes.
So this 70%, 0.7 of this 0.6 is what? So this 70% is probability of a person playing cricket given that person is a boy. Does that make sense to you?
Yes, ma'am. Yes,
Ma'am.
ma'am.
Ma'am, in this case, because we know the number of boys, we can just put 60 into 70 by 100 and get the answer.
Do it for the football. So there's something else. Do the same thing for football. I give you 5 minutes.
Okay.
Just as we had cricket, do it for football. Tell me, what is the probability of a person playing cricket now? Give me a minute. I'll have a sip of water,
60.
please.
Sure.
1 second.
0.62.
Sorry. Yeah. What is the probability of person playing cricket? Probability of C given G into probability of G plus probability of C given B into probability of B. Agreed?
Yes, ma'am.
This is
Yes, ma'am.
point. This is point 4. What is point C into G? Is 0.6 into 0.4 plus 0.7 into 0.6. Is that right?
Yes.
0.24 plus
0.42.
4-2.
0.66.
Yeah.
So far, so good.
Yes.
Yes, ma'am.
Similarly, what is probability of a person playing football? Probability of football given girl into probability of girl plus probability of football given boy into probability of boy. Same thing.
Yeah.
Now what is this probability of football given girl from the data? 50% of the girls
0.5
play
0.5
football.
into 0.4
So this
0.5
will
into
be 0.5
0.4
into 0.4. What is
plus
40% of
point-
the boys play 0.4 into
0.6.
0.6. So 0.2
20.
plus
Yeah, plus
0.24,
0.44.
0.44. So far, so good.
Yes, ma'am.
So now I'm going to just write down those two things. Probability say is 0.66 and probability of football is 0.44. So far, so good.
0.44. Yes, ma'am.
Yeah. Now,
Yes, ma'am.
what is this 33%? 33%. So what is the conditioning event here?
P of F by C.
F by C or C by F? 33%
C by F.
who play
C by
football
F.
play. Probability of
P by F.
given a
C by
person
F.
out of the people who play football, how
F
many
by
play
Q.
cricket? It is
Guys, please,
0.33.
0.6.
Is that
Yes,
clear?
ma'am.
Yes,
Yeah.
ma'am.
Yes, ma'am.
Now,
Yes,
what
ma'am.
is it I want to know? A student is chosen randomly and it is known that that person plays cricket. So what is the information that is given to us? That a person plays cricket. I want to know what is the probability that the person plays football. This is what I want to know.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Now, what is this? From
P
our
of F
definition, this is
intersection
probability
C
of
by
F intersection C divided by probability of C.
Yes, ma'am.
Now, do I know all these terms here? I know probability of C, but I do not know what is probability of F intersection C. But I know probability of F intersection C can be written this way.
into.
I can do this.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
What, do I have what is probability C given F?
Yes, ma'am.
Yes,
What
ma'am.
is that?
0.33.
What is probability of F?
0.44.
0.44.
What is probability of C?
0.66.
What is
0.66.
this probability of F given C?
0.33.
33.
Can you please mute, please? Probability of 3 into probability of 4 divided by probability of 6. What is this?
0.22.
0.22. And that is your answer. Is that clear, please?
So, ma'am, anytime when we are converting this intersection into the conditional probability, probability of A given B will be written as the B given A into P of A again.
That is your multiplication rule.
Okay. So every time I get confused.
This is the multiplication rule. Irrespective of independent, if they are independent, then this just reduces to probability of E.
Okay.
So you have the this one product. Is that clear?
And ma'am, we can refer that as P of E multiplied by P of F by E also, right?
Yeah. We can do that. Okay.
Yeah, madam, one question. See, in this situation,
You have very low volume, please.
oh, okay. Is it okay now?
Okay.
See, we are up. What if we want to find out the probability of a person who is not playing one of the games? Because we always, how do we, if we turn it the other way for the same problem?
Okay. So can you explain with respect to this?
Here we are trying to find out a student who is chosen randomly, and it is, he plays cricket, and then what is the probability that he plays football, right? What if we turn it saying that we know the student plays cricket, but what is the probability that the student does not play football? Is there a way to?
Yeah. So probability of F given C plus probability of F complement given C is equal to 1.
Okay.
Okay, because conditional probability is also a probability. I know probability of F plus probability of F complement is equal to 1.
Yes.
Okay, so I can answer the, this is what you wanted to know?
Correct.
Okay, so the probability if, but the point is don't get confused to F given C plus probability of F given C complement.
Okay.
They're different, okay? These are not the same. Is it clear? You're conditioning it on the same thing because you're, see, basically conditional probability means that you are working on the smaller subset given an event, right? So now this, suppose I know I'm tossing a coin, HH, HT, TH and TT, and I'm conditioning it on head in the first toss. Now this becomes some sort of a restricted sample space to look at the second event. You agree?
Yeah.
Yes, ma'am.
Yes, ma'am.
So this conditioning event cannot change. This conditioning event cannot be C here and C complement here. That's what I want you to understand. Is that clear?
Okay.
Is that clear?
Yes.
So now
Yes.
you can, if you
Yes.
define, so here I can define complement because the full set would have probability. If I'm conditioning it, it's going to be equal to 1. Is that clear?
Yeah. So the conditioning has to be the same if you have to do any of these. Okay.
So define the complements. Is that clear?
Yes, ma'am.
Yeah.
Ma'am, that formula, can you please just reiterate once again? That multiplication of the B given C and multiplication of the two independent variables. Can you please repeat that one, please?
This one?
Previous question. In
This one?
इससे पीछे पहले वाला हाँ इसमें this one and this
yeah, the conditional probability says probability of E conditioned on F is probability of E intersection F divided by probability of F. So far so good. This is from the
Yes,
definition of conditional probability. Now I can cross multiply these terms and I get probability of E intersection F is probability of F into probability of E conditioned on F. Is that clear? This holds for every pair of events. Is that clear?
Okay.
Now if E is independent on F, then it just reduces to probability of E. So I get the probability of intersection is the product of probabilities. Convinced?
Yes, ma'am. One quick question. This problem which we are looking at for football and cricket.
Yes.
Can we solve that using the intersection method, as in having a table where you can have a
But you need to understand what are the probabilities. See, the table, everything gives you the same thing. So what is the table? In the table, I had girl, boy.
Yeah.
I had
and then
cricket,
we had
non-cricket. This was
and
40,
you can have football, non-football.
I can similarly I have girl, boy.
Yeah.
Football, not football. But the problem here is football and cricket, are they mutually exclusive?
Yeah. And they are not. No, they can. No, if you can play cricket, it's not necessary. Yeah.
You got your answer? These tables worked for mutually exclusive, right?
Exclusive. Okay.
Football and cricket?
Yes.
They're not mutually exclusive. So
got your answer?
Yeah.
Okay. Ma'am, can you go 2 slides back?
This one?
One more. No, there was one conversely one.
This one.
Yeah, here, ma'am, the two equation looks same, right? Then and the conversely part.
No,
The second
they
one was
read the sentence. If E and F are independent, then the product of that is the probability of intersection is product of probability. Conversely, if product of of this one is equal to, then they are independent.
One is condition, the other is deduction.
If and only if. It does not need to be same for E intersection F intersection G. That's why independence of three events is different.
Okay, ma'am.
Okay. Is this clear, please? Yeah.
Yes, ma'am. Yes, ma'am. Thank you.
Great. Okay. So now I will just illustrate a very simple way to understand, which is the concept of probability trees. This probability trees was not covered as part of your lectures, but I'll just help. This will be one way to understand how to come up with probabilities of trees. For example, I toss a coin one. What are the possible outcomes? It's a head or a tail, and I can write it as a head and a tail. These are the two outcomes, and each one of them have the same probability if they are mutually exclusive and if it is a fair coin. So far so good. Now if I toss a coin twice, okay, I can have this as my first toss. My first toss has two outcomes. My second toss also has two outcomes. So how many leaves do I have eventually? This is a head and a head. This is a head and a tail. This is a tail and a head. And this is a tail and a tail. Is that clear?
Yeah.
Yes, ma'am.
Now, this probability is half. This probability is half. Now, what is the chance of a head appearing given there was a head in the first chance?
1/4.
1/2.
1/2 only, right? Head appearing given. So this was independent, right? This is again half. This is again half. This is again half. So the probability of a head and head appearing is again by our multiplication rule. This is a probability of head appearing given head in the first toss into probability of head, which is 1/4, 1/4, 1/4, and 1/4. Let's look at another example where I am picking a ball from 3 black and 4 white balls. Okay. Now, what are the two outcomes that are possible? I'm picking one ball from a bag of 4 white and 3 black balls. What are the outcomes that are possible here?
Black and white.
So my sample space is black and white. What is the chance of picking up a black ball?
3/7.
3/7.
3/7.
Chance of picking up a white ball?
4/7.
So I'm writing the black ball and a white ball. Okay. Now I have, if I pick up a black ball, I'm picking up a ball from this bag, which has 3 white and 6 black balls. So now what are the possible outcomes I have here? Again, I'm picking up one ball.
White and
Black or white.
It can either be black or white.
What is the chance of picking up a black ball from this
6/9.
6/9.
6/9.
What is the chance of picking up a white ball?
3/9.
3/9.
Now, what is this 3/9? It is picking up a white ball, okay, from the second bag. Given that you picked up a white black ball from the first bag.
Okay. Yeah.
Right. Now, is similarly, what are the outcomes here? A black ball and a white ball. What is the probability of picking up a black ball in the second ball? This one.
5/9.
5/9.
And this is
4/9.
4/9.
Is this clear? Now tell
Yes,
me,
ma'am.
suppose this was a B1 and a W1. This is B2, this is W2, B2, W2. B1 is picking up a black ball in the from the first bag. And B2 is picking up a black ball from the second bag. Given I have picked up a black ball in the first ball. Is that clear?
Yes, ma'am.
Yes, ma'am.
Now, are they dependent or independent? Having a black ball in the second draw, does it depend on whether you picked up a black ball in the first draw ball or not?
No,
Independent.
they are independent.
See, no. See the problem very
Dependent.
carefully. What is
It is
the chance of me
dependent.
getting a black ball
Dependent.
in the second draw, or if I have picked up a white ball in my first draw?
Because if we
It's
put the
they are
ball in
dependent
the
because
first draw,
both the
It's 5
bets are
by 9.
different.
This is 6 by 9, right?
And
Yeah.
this is dependent on picking ball on bag first.
ma'am,
Ma'am,
this
they
is
are dependent
without
because both the
repetition.
bets are different.
Yeah, the bags are different, right? So the bags are different. So it is dependent, right, on what was your outcome in
Yes,
the
sir.
first one. So what
Okay.
is this event? This is picking up a black ball in the second, from the second bag, and or second bag money, it's a second sequence, right? The bags are different. If it is a white ball, you go to a different second bag. If it is a black ball, it goes to a different second bag, right? So
Okay,
this
okay,
is having both
Yes, ma'am. These are
black
two
balls.
scenarios.
This is having a black in the first and a white in the second. This is having white in the first and black in the second. And this is having both white balls. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
And I can just multiply the probability along the arms. So if I multiply the probability along the arms, you can see that this is 3 by 7 into 6 by 9. This is 3 by 7 into 3 by 9. What does this probability add up to? These two probabilities?
$18 by 63.
No, it's
3 by 7?
3 by 7.
yes, yes, black ball.
What does these two probabilities add up to?
4 by 7.
4 by 7.
4 by 7.
Probability of a white ball. So again, you can go back and check your multiplication rule and your contingency table. These are the marginal probabilities of a white ball in the first, this one. Is it clear?
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am.
Yeah.
And this method is quite simple.
Yes.
Everything is the same thing. It's just that we are demonstrating it using a tree, graphically representing. I'm not doing, see, actually this is the same thing. This is a probability of a black ball given a white ball, black ball in the first thing, the 6 by 9, into probability of a black ball in your first, which is 3 by 7. And this is probability of B1 intersection B2. That's it. How did I get my 6 by 9? By looking at the conditional probabilities. That's
Yes,
all.
I'm understood, but the way that you are doing is just amazing.
Okay. So that is what we can do. Similarly, this is 3 by 9, this is 5 by 9, and this is 4 by 9. So whenever you have problems of this kind, if writing it down as a tree helps you, please do it. It will be, so whatever suits you, so let's look at another problem.
Ma'am, I wanted to ask, like the problem about the boys and girls and the football and cricket could it also be reduced to the tree form?
Everything you can do it, right? Girl and boy. So this is a girl, this is a boy. This is 60 by 40, 100. This is 40 by 100. Cricket, given a girl, you know what is this one? Okay, you can do it.
It's easier to understand once it's in visual form.
Okay, do it. If you have a problem, you can ask the team. Okay. Is conditional probability always independent? No. The entire thing of conditional probability is lost if you think that. No.
Excuse me, ma'am.
See, I'm not following. See, the multiplication rule is there irrespective of condition. See, probability of A intersection B is probability of A into probability of B given A. Probability of a black ball in the first bag and a black ball in the second bag is probability of a black ball in the first bag into probability of black ball in the second bag conditioned on black ball in the first ball, right? These were dependent events, right?
Yes, ma'am.
Is it clear, please?
Yes, ma'am. Yes, ma'am.
Ma'am, I can.
Yeah.
Hello.
Yes,
Ma'am,
please.
if there are 3 branches, then can we calculate probability
As
from this
long as
method?
you are, suppose now again I'm
Suppose
talking
we have
about,
a
I can do
green
it.
ball.
No?
Green ball.
I'm doing it for rolling a dice. First
Yes,
outcome is 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. This outcome is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. This is with 1 by 6. This is 1 by 6. This is 1 by 36. Is it clear now?
Ma'am,
Okay,
You can do
ma'am.
it?
Is it clear?
Ma'am,
Clear,
this
ma'am.
tree concept will work only when the head and tail, these things should be mutually independent. Na? Each
Mutually
branches should be
exclusive.
mutually independent among themselves.
Yeah. Otherwise, these should add up to 1, and they'll add up to 1 only if they're mutually exclusive, not mutually independent.
Yes, ma'am.
They should add
No,
up to
ma'am,
1 means they're exclusive events. Don't get confused between disjoint and independence. Is it clear?
Yes, ma'am.
Yes, ma'am.
Is it clear?
Yes,
No,
yes,
ma'am.
ma'am.
Just repeat it again.
Okay. So I think
Yes, ma'am.
I have pretty much covered whatever I wanted to do. If there are any specific questions I can do, or Ishan, is there anything you want me to, Ishan, Mayur, is there anything you want me to this one?
Yes, if you can elaborate the difference between the conditional and base theorem.
Okay.
Yes, ma'am. How can we identify a problem can be solved using Bayes theorem?
Okay. Now, if you look at this Bayes theorem, right? Okay, let me take another example to explain this Bayes theorem. Just give me a minute. Let me explain.
Ma'am, even I didn't understand law of total probability.
One second, let me look at a. Since I have the sample space with me of rolling a dice, okay. I'm again defining E to be the sum equal to 7. Okay, and F to be the sum is equal to 6, and G to be the event, the first row is a 2. So far so good. I'm going back to the same thing.
Yes, ma'am.
Okay, right. Now, one thing I can do is, suppose I'm looking at a sum of 7. I want to know what is the probability I get a sum of 7. I can write it as probability I get a sum of 7 given the first outcome is a 1 into probability it's a 1 plus probability of getting a sum of 7 given the first outcome is a 2 into probability of 2. Can I do it this way? I'm breaking
Yes,
it
ma'am.
out to this way.
Yes. Yes.
So what is the whole thing? I'm looking at what are the outcomes. I'm getting a 1, I'm getting a 2, I'm getting a 3, I'm getting a 4, I'm getting a 5, or I'm getting a 6. These are mutually exclusive. Yes. And getting a sum of 7 can happen both with 1, 2, 3, 4, 5, 6.
Yeah.
And they are also independent.
So what is the probability of getting a sum of 7 given I had a 1? What is the only outcome that satisfies that?
1,
6.
1, 6. So that is just 1 by 6. What is the chance of
1.
getting a 6? This is again 6 by 36. Probability of getting a 1.
Yes, ma'am.
Yeah, ma'am.
Yes,
6 by
ma'am.
36. Okay.
Again, this is 1 by 6 into 6 by 36. So everything is 1 by 36. 1 by 36 is 6 by 36. So probability of getting a sum of 7 is what? So
6
again,
by
6,
36.
which is 1 by 6.
1 by 6. Yes.
Yeah.
Is that clear?
Yeah, ma'am.
Yes, ma'am.
Everybody clear with that?
Yes,
Now
ma'am.
let's do the
Yes,
same
ma'am.
thing for sum of 6. Can we apply that for sum of 6?
Yes, ma'am.
How can you do it for sum of 6? Probability of getting a sum of 6. What are my mutually
Ma'am, we can
exclusive
do it
events
till
here? 5, right? It is, so it would be a 1 by So again, what are the
1 by
mutually
30.
exclusive events? Getting a 1, 2, 3, 4, 5.
Yes, ma'am.
Can I do it? First of all, tell me, can you do this way? What is
Yes,
the
ma'am,
chance of getting a 6 given it was a 1? What is that
into
chance?
probability of 1.
So what is the probability of 1 here?
6.
6
by
36.
Here is,
6 by
see, but
36.
the problem here is, are F1, F2, Fk exhaustive? F1, F2, Fy. So that is the first thing. F1, F2, Fy are not exhaustive.
Exhaustive.
Is that clear? I could do it for 7, but I cannot do it for 6. Is that clear, please?
Yes, ma'am.
Yes, ma'am.
The
Understood.
first thing when I want, is the law of total probability now clear?
Yes,
Ma'am, is it meaning that I can get 6 at let's say if I'm tossing the flipping the dice, so I can get the 6 at one event. So is this the meaning that you are saying? It is
No.
not.
What I'm saying is, I can, if my first throw is, I can get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. This is, I'm calling F1 is getting a 1, F2 is getting a 2, F3 is getting a 3, F4 is getting a 4, F5 is getting a 5, and F6 is getting a 6. So far, so good. So what is that I need from F1, F2, Fk? They are mutually exclusive. Are they mutually exclusive?
Yes, ma'am.
Are they exhaustive?
No, ma'am.
Yes, ma'am.
Here, in this case.
In this case, yes.
In this case, yes.
Yeah, in this case, the
But
first
if
case
I
they
have
are
taken
exhaustive.
F1, F2, Fy, they are not.
Their union should form a sample
When you
space.
are saying
So it should form
not
the sample space. It's not happening, right? It's not exhaustive,
Yeah.
right? So I cannot apply the theorem there. That's
ma'am,
law.
sorry, ma'am. Actually, here when you're saying exhaustive, what exactly you mean to say? Exclusive and exhaustive.
F1 union F2 union F3 union F5 should be equal to your entire sample space. That's what I mean.
And their intersections should be 5. That means it's
Yeah, that
mutually
mutually exclusive means that they are this one disjoint, and the entire union should be equal to the sample space. Is this clear, please?
Yes, yes,
Here
yes.
events F1 to F6 is independent also, right?
What do you mean by independent again? If I get a 1, can I get a, they're disjoint, but getting a 1, is it dependent on getting a 2? Is it dependent on whether I got a 1 or not?
No, ma'am. Yeah.
You think
It is
about
dependent.
it. Again, you go back, the conditional probability, the
yeah.
intersection is 0, all of this.
Correct.
See, you just have to keep working it again and again and again. Okay.
So they are not dependent. No, now in this case, getting a 2 and getting a 1.
They are dependent because if
If I get a 2, can I get a 1 also?
Yeah.
It's mutually exclusive in some sense, right?
Yes, ma'am.
I mean, if 1 happens, 2 cannot happen, and if 2 happens, 1 cannot happen. So in a way, at the same time, I mean.
So they are independent, no?
They are dependent, right? They are disjoint in a way.
They are disjoint.
Yeah.
Okay. Right.
Yeah.
Okay. So now the question, which is this clear till here? How I got a sum of 7?
Yes, ma'am.
Yes, ma'am. Yeah.
Okay. So what this says is this probability of E given F1 into probability of F1. So now let me, all of you have seen game shows?
Yes, ma'am.
Now, there is a very famous game show called the Monty Hall problem. I do not know whether you're aware of it.
I'm not aware.
One second. Let me try and see whether I can find, I think I should have a slide. Just give me a minute, please. To explain the base theorem as what you have told, let me see whether, okay, yes, I'll see whether I have the slides for that. Okay, yes. Are you able to see my PDF?
Yes, ma'am.
Yes, ma'am.
Okay, so now let me look at. Are you able to see what is called a Monty Hall problem?
Yes, ma'am. Yes.
Yeah. Okay, this is from another course I teach. So behind one of these doors is an expensive item. Okay, such as a car or gold. Okay, and there are inexpensive items behind the remaining two doors. Okay, you are asked to choose one of the doors. So now prior, what is the chance of you choosing any one of the door?
1 by 3.
1 by 3.
1 by 3.
So so I can choose door 1 or door 2 or door
Or
3, and all of them have the same probability. 1 by 3, 1 by 3, 1 by 3. So far so good?
Yes, ma'am.
Yes, ma'am.
Now what happens is the contestant, suppose you are choosing door 1. Okay. Now what happens is that game host is going to open one of the remaining two doors. Okay. So assume the game host opens the door 2 and you find a goat behind it. Okay. Now the question is, would you change your choice or would you not change your choice?
No, madam.
Why not?
Change.
No,
Why,
madam.
why?
You can change my choice.
Why?
Because it's still the if door 1
See,
is
the
good, right?
probability of a car behind door 1 is 1 by 3. Probability of car behind door 2 is 1 by 3. Probability of a car behind door 3 is also 1 by 3, right? Initially, when you have nothing known. Is it clear? So these are what I call my prior probabilities. Okay. Now I'm saying that there is a goat behind door 2.
So the probability becomes 1 by 2.
1 by
What
2.
would happen to your probability? So that is what the Monty Hall problem is about. Okay. So what you want to try is, so this is how you are going to use the conditional probability. So given the extra information, what is the extra information that is given to you now?
The door 2 is
Door 2 is open.
Giving conditions good.
Right.
Yeah.
The door 2 is open. So now, if there is a car actually behind door 2, will the host open the door?
No.
No.
Right. So now you are having extra information. Okay, behind this door there is a goat. So now your extra information. So your posterior. So what happens because of this information? That's what Bayes tries to solve. So let's look at another simple problem here. Okay. Go and look at the Monty Hall problem. There is so much available about the Monty Hall problem and how people have solved it. It's very, very interesting. Now let's look at this problem. 3 manufacturing plants supply 20%, 30%, and 50% of all shock absorbers used by a certain automobile manufacturer. Okay. Records show that the percentage of defective items produced by A is 3%, B is 2%, and C is 1%. What are the mutually exclusive events here?
Supply of ABC.
ABC
Right.
and
So I
defective
can
and
have
non-defective.
a shock
ABC.
absorber can come either from A or
B
from
or
B
C.
or C. I cannot have a shock absorber coming from both A and B, or from both B and C, or from A and C. A
Yeah.
shock absorber can come either from A or from B or from C, right? But I can have a defective item which is coming from A and B and a C.
Yes,
Is that
ma'am.
right?
Yes.
And the probability of me having a defective item is probability of a defective and A, that is this shaded region.
Yes.
Yes.
Yes, ma'am.
This region
Yes, ma'am.
and this, right?
Yes,
These 3 regions. Now this is what is the law of total probability. So now what is the probability of my defective item? It is the probability of a defective item given it comes from A into probability it comes from A. What is the probability that I find a defective item if it comes from A?
3%.
3%.
3%.
What is the chance of me coming from A?
20%.
20%.
So this is going to be 0.03 into 0.2.
2. Yeah.
Similarly, what is this?
0.2
0.2 into 0.3.
Very good. What is this?
0.01 into 0.5.
0.01 into
0.5.
Fantastic. So you all know what is the probability of finding a defective? And this is nothing but you have applied the law of total probability. That's it. Forget about if you don't like the law of total probability, you know how to find the probability of a defective. Is that clear?
Yes, ma'am.
Right? Okay. Now, initially the probability of me getting a problem, that is a shock absorber, what was the chance that I choose a shock absorber? What is the chance it comes from A?
20%.
20%.
It comes from B?
30%.
It comes from C?
50%.
Now I pick up a shock absorber, I find it is defective. What is the chance that it has come from A? Is there a difference between the earlier question and this question?
Yes.
Now what is the extra information that you have given?
The shock absorber is
that it is
defective.
So now this is going to be probability of A intersection D divided by probability of D.
Yes, ma'am.
The same as probability of D given A into probability of A by probability of D. This I can find out, and this is precisely what is your base theorem.
Yes, ma'am.
The denominator is your law of total probability, and this is just from conditional probability. Is that clear, please?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Clear. Yes, ma'am.
So Bayes theorem is nothing but the conversion of that intersection we did into the conditional probability, right?
That is law of total probability. Bayes theorem is a posterior probability. See, initially, so this problem, what is it? I choose a shock absorber. I'm getting 100 shock absorbers in my factory. I choose one at random.
Okay.
Okay. What is the chance it has come from this manufacturing plant B?
30.
30%. So initially, prior probability without any extra information is 20% come from A, 30% come from B, and 50% come from C. This is prior probabilities.
Okay.
Probability of
Here-
A, B, and C.
Here
Now
we are
I
given the posterior. Here we are given the post information.
Yeah, the post information, if I am picking a shock absorber, I find it is defective. Now I want to know what is the chance that absorber came from A.
Okay.
Is that clear?
So
Yes, ma'am.
The extra information, just as the extra information in the Monty Hall problem was, there is a goat behind a door. Right?
so it is so we can find the same for either B or C also, no?
Yeah, you can do probability of B given D. You can find out these are what are called posterior. Probability of A, B, and C are
So
prior.
we use these Bayes theorems applications when finding these probabilities. A by
Yes.
D, B by D, and that's it. Okay.
Those are called posterior probabilities.
Okay.
Madam,
Yeah.
here this problem talks about what is the probability of the part came from manufacturer given the part is defective.
Yes.
What if I know previously I was asking something right about the part is not defective. What is the probability that it is coming from one of these or a combination of these? I think those kinds of questions are also possible, right? We should be able to solve that also with this.
See, typically, then you'll need to find out what is the chance you don't have a defective item. The conditioning probabilities have to be the same. You can solve it. Only thing you'll have to find out what is the probability of not finding a defective item.
Okay, because if I pick a part and then if I say what is the probability that this part is coming from, but it is not defective and it is coming from a certain manufacturing plant B or C,
So you find out what is the probability of me not finding a defective item. So I can, same thing with the not defective can also be done.
Yeah, but should it be D complement or something? How do we?
Yeah, I have written D complement only, right?
Yeah.
Okay, and the same thing I can do it with the D complement. From this I cannot find. Given this I cannot find. I need to do it from here. Is it clear?
So from the same numbers we won't be able to see. That's what I was
From
getting.
here, no. From here, see, if I know A given D, I can find out A complement given D. That is what is the chance that it comes from B or C given it's a defective. That's what I can find. The conditioning probability, the event has to be the same.
Okay. Because it's somewhere I was looking for some problems on YouTube. Somewhere I found one more question which was asked where they are saying what is the probability when I pick up a part that it is not defective and it is coming from a union of B and C.
Yeah, you can manipulate this. You can find out what is the, you can apply all these things and find out. Okay, that can be done stepwise, not an issue.
Ma'am, here we can't find probability of A such that D complement is given.
D complement.
Yeah.
If you know probability of D complement is probability of D complement given A into probability of A. I know what is probability of D given A.
Yes.
If I know probability of D given A, do I know probability of D complement given A?
Yeah.
Then I can find it out.
Okay.
Is it clear, please?
Yes, ma'am.
Okay, always the way is write down what are the mutually exclusive. Try and see this equation and get to the law of total probability and then work out the Bayes theorem. I hope this is slightly clearer than what you had earlier. Okay.
Yes, ma'am.
Yes, ma'am.
Okay. So Ishan, anything else? Ishan, Mayur?
No, ma'am. I think we have already exceeded the time.
Excuse me, ma'am. Ma'am, it's my humble request that can you please take one more session of question problems?
Pardon?
Ma'am, just before the quiz 2.
I think that's already been scheduled, right? Ishan and see, I think my team is doing a wonderful job. Whenever they want me to step in, they call me. Okay, and you tell them if you want them, I can always call. Do it. Okay.
If you will take our session, that's
Ishan and Prashant. Actually, they are doing a good job.
Yeah. So they are doing a wonderful job. Okay. So yeah, I will share the PDF, but the PDF is nothing new.
It's just we can quickly scan through all the concepts in like one go, and given we have only 1 week left for the exam, so it would be useful.
Ishan, I'll send it to you, and you can just
save the PDF with your working.
Yes.
Pardon?
You save PDF with your working in it.
My working, I have not saved it. I'm sorry about it. Okay.
Actually, these slides are same as the lecture slides, which are
that's it. That's what I'm saying.
Access it. Yeah.
That's it.
Nothing very different. Okay. Okay. Right. Okay.
Hello, ma'am.
Yes.
Hi, ma'am. Thanks for your session. I shared one question. Is it possible for you to discuss one question from today's mock?
I'm already very fatigued today. I'm sorry. Okay.
No problem, ma'am.
I'm sorry. This is my 6th hour of teaching today, so I think
Absolutely, we
totally.
understand.
I'm sorry about it. And tomorrow, I think we are meeting a few of your batchmates, and I do not know whether you're batchmates, but
it's diploma students.
Diploma students, right? Okay, that's right. Okay, right. Thank you all. I hope it was useful. Okay.
Very useful, ma'am.
Thank you, ma'am. Very useful, ma'am. Thank you so much.
Thank you.
you, ma'am.
Thank you. Bye, everyone. Take care.
Bye, ma'am.
Bye. Bye.
Thank you very much, ma'am.
Thank you. Thank you. Thank you all. Bye.
Thank
you, ma'am.
Ishan.
Yes.
Can we continue, Ishan?
Yes, ma'am. Thank you, ma'am, for the session. I will continue from now.
Yeah.
Sir, can you please explain this today's mock question, the 5-letter, how to solve?
I shared the same question. Actually, the question has vanished.
Yeah, I agree.
How I proceed, how I started with because it is telling it is in ascending
We
order.
get the solution PDF.
See, mock test it tomorrow from 3 to 7 p.m. Okay. So those who have not attempted can attempt it tomorrow as well.
Same mock test. What we did today.
Like
Yeah,
I
we
did not
today
receive
and we
any
are not able to.
notification.
The email has been sent to everyone. Even I received it.
I didn't receive anything in neither in the announcement, and I can't even still see it in my.
Yeah, it is not in our portal, sir. A mock test.
I can't see it anywhere. I've been trying the whole day. I didn't see anywhere any
one
announcement
minute,
or
one
in the mock even.
No, the mock event came up, but it vanished all of a sudden after the time was
Yeah,
out.
after that time it's vanished.
So will it come back?
Do we get the solutions? Do we get the solutions for this mock test? What we
Yeah,
did
after
today?
the mock session on Friday, you will get it.
Okay.
Okay.
Sir, so it will be available.
Response we also have.
Yeah,
when
mock
it
test it will be made available later as a practice assignment. Okay.
Sir,
So
tomorrow it will be available from 3 to 7. It will be the same mock.
I'm not sure about it, but yeah, most probably yeah.
But today at what time was it, sir?
It was 5 to 6 p.m. for stats 1.
Because we saw the mail, but when I checked in my portal, it was not there. Many people had complained about the clash of the mock and ma'am's class.
Yeah, we have shifted it.
Yeah.
Straightforward. In the 5 minutes, we have shifted it. I think.
Ishan, was there some confusion for stats 2 also? The mock?
I'm not sure about stats 2, but
No.
yeah, stats 1 and maths 1 were colliding with MAM session. As far
Yeah,
as I'm
okay,
aware.
fine. Thanks.
So we have shifted it.
So we should wait till next Friday for the mock test solutions.
Yeah, you can try and try as many.
No, because Sunday is only the exam, right? Quiz 2. If we get earlier, it would be better.
Yeah, the solutions. See, there is nothing new in the mock question. As if you try it yourself, I think you will be able to learn better. Then go through the solution.
Ishan, one more thing. What about the assignment deadline for that is for Wednesday?
For week 10?
Yeah.
Yeah, currently it's Wednesday, but most probably it may postpone. But yeah, for now it's Wednesday.
Okay.
Sir, for me, the mock test has not vanished. It is.
It will reappear
even now.
tomorrow. Yeah, it will reappear tomorrow.
Tomorrow at what time will be the mock test?
I have to discuss with the portal team, and I will. It will be made available, so it won't be vanished.
Mock test available in the dashboard, ma'am.
Actually,
Yeah, it will be
this they are planning to take
tomorrow's
for
mock-
graded assignment, right? The mock test. They are planning
No. Today's mock test was just to give you the idea of like how to attempt it in 1 hour time.
Okay.
The tomorrow is a catch-up assignment. There are many students whose
Correct.
5 out of 9 score is not exceeding 40. So it is for them to attempt and get their scores.
Okay. No, actually, tomorrow's mock test at what time?
It's
Also
3 to
maths
7
also is-
p.m. Yeah, but
Maths?
it requires only 1 hour to solve that. You don't need complete 4 hours.
Yes.
So it doesn't matter if it's colliding.
So that will be considered as a graded assignment, is it?
Yeah.
Five out of 9, that is for eligibility for final?
Yeah. Those whose score is getting short by 4 marks, they can try to get the scores there and proceed.
The level of the questions will be the same as today's mock.
Yeah.
So today's mock is not related to the quiz on 13th, is it, sir? Or just the
It is related to it's the same pattern.
same
And
pattern?
actually, sir, what will be the
The same
level of
pattern
the-
exactly. 4 optional question would be the same. Everything is same. Almost.
the level of
What
the-
about the 0 marks question? They are that were there.
Yeah, if you get the answer wrong to that NET questions, we will check the steps. Like if you have marked the correct steps, you will still get 1 or 2 marks, and you won't lose all the 4 marks for that question. It's something like that.
Got the correct answer, then it won't increase.
Yeah, if you have answered it correctly, then we won't even check your step-wise question.
Okay.
Sir, in case like I was facing problem, I can't see the mock in my portal. What if that happens even tomorrow? What am I supposed to do?
It is available. Even I have checked it myself. It was available.
Is it available right now also?
No. Now it's vanished. It will be made available
In any case, I'm
later.
not receiving any emails from the support team at all for anything. Absolutely nothing.
Is
I
it for
don't know what's
everyone or?
No,
I do not.
I got the mails.
Receive all of the
required
mails.
emails.
I don't receive any emails. I check my spam, everything.
Can
Which
we
mail you are
first?
checking? Sorry, I
Can
need to interrupt here. You should matlab, go to with group and just subscribe that announcement section. Definitely, it will be available for you all related to
How do I
communication.
subscribe to the announcements? I'm
I
sorry.
think Ishan sir, please.
Initially, they gave a link during the start of the term. They gave the link.
Yeah. Well, the
That
start
is
of
I must have missed out on something.
if you don't subscribe, then you won't get that.
Ishan sir, there is a subscription. If you go now, my group section, there is an announcement section and join date subscriptions are there. Each mail, if you subscribe for each mail, definitely will receive their conversations and all. Maybe I think you just put it that no emails. That's the
No,
reason
but
you are
then
not
these
getting.
would be that is for the forum, right? But I mean, this would be specific mails that are being posted to us.
No,
from-
you send a mail to support.
Yeah,
Actually,
I mean-
every 15 days, even the support should come online and discuss the issues.
You can mail and call them anytime.
The call it won't work.
They are available all the time. They will be attending a lot of calls. See. Okay.
Okay. And one more, Ishan, this today's mock test, the level of quiz 2 will be on par with today's mock test, or it will be even higher?
We tried to keep it as same as possible, as similar as possible. It won't be
Because
that.
this was